think we should be set. Okay, so the last thing that we were looking at yesterday, day before yesterday, was this idea of abstracting the details of an implementation using abstract types. And the stack that we had implemented with abstract types, we called it abstract stack, right? And we had this concrete type internally in the stack implementation, which said that the abstract type alpha t is the same as alpha list. And we included the rest of the stack definition as it was previously defined. The only thing that makes the type abstract is that the abstract stack type that we have here, which was defined in this place, the type here is left abstract. We just say that, oh, this module has a type called quote AT. We don't actually give you any other details about quote AT, right? And the only operations that you can do with quote AT are the ones that are defined here, right? So that is what gives us this abstraction. Yeah, so what does abstraction mean, right? So sort of look at principles of computer design and so on. So people keep repeating this term called abstraction, and how computer science is all about finding these abstractions and making beautiful abstractions and so on. I mean, the key idea is this, right? You sort of build interfaces, right? In this case, we build it with abstract types, and these interfaces are contracts between the implementer, the one who, say, in this case, implements the stack, and the user of the stack, right? And this interface sort of clearly defines the contract. That's the only contract that the implementer and the user will have to respect. In particular, because the types are left abstract, the user cannot violate the API. So, for example, in a language like OCaml and Java, which have strong type systems, there is no way to tell you what the internal structure of the list is anymore, right? So the stack is anymore. And this is quite important, right? So it says that once you implement the stack, there are only a fixed number of ways by which the API can be externally used, and that is enforced by this abstract type, and that is exposed by this interface. And what is the other benefit for implementer? So the implementer can transparently change the details of the implementation. Suppose I come up with a better implementation of a stack, right, which gives me better, more performance. As long as the API is retained the same, I can change the implementation of the stack, say from a list to an array. Let's say I know that the only place where this stack is used is in place where the maximum stack depth is, say, 1024, right? I can pre-allocate an array which is of size 1024 and use pointers, use indexes, right, into the array to note the top of the stack. This is much nicer. This is likely to be more efficient than using lists, because every time you add an element to a list, you're actually allocating this new node, right? So just like linked lists, when you want to add a new element to a linked list, you allocate it in memory and then you link it, right? So we sort of go for a better implementation, but the idea is that as long as the API is preserved, the implementation can happily change and evolve and so on. So in order to show that in practice, in the case of using abstract types that we have defined here, so here is an implementation of the stack using user-defined list. So the earlier stack used the built-in lists, right? So all I'm doing here is I'm defining my own list type, and this is the list type, right? This is what we have seen earlier. And I'm saying that alpha t is this list type. And I'm going to use this list as a stack. So an empty stack is just the nil variant. Depth is just a recursive call that keeps adding 1 until you reach nil and you return the accumulator. This is just the same function as what you would implement to find the length of the list. Yeah, that's a tail recursive one. So I define depth here. Push and pop are simply cons for push, and the usual pattern match and destruct for pop. So if the list is empty, um, uh, if the list is nil, then we return none for popping. Right? There is no element to pop. And if it is cons, then you just return the pair of the element that is popped and the tail of the list. Right? And is empty just checks for nil, and if it is nil, return true. So this particular implementation, right, has so this is just the module definition without the abstract type on top. So the module has implements the same function, but it is also the case that this module has the same type. Um, this module can be restricted in the same way, just as we restricted the abstract stack earlier, using the abstract stack type. So um, the module, I call it variant stack. Okay, and what I do here is I define a module called abstract variant stack, which is the same as variant stack, except that I restrict the type using the abstract stack type that we defined earlier, which does not expose the details of the implementation, right? And oops, I think I need to run a few of these things to get working. So let me run this type. I think this would work. So this abstract variant stack also has abstract stack type. What does this mean, right? Wherever you expect to use abstract stack type, you can happily replace the earlier implementation of abstract stack with this version of abstract variant stack, and the user code will not be able to tell the difference because they provide the same API, right? So that's what the abstraction provides you. So it gives you the flexibility for the implementer to independently change the implementation. And by clearly defining the interface, you can sort of use the interface as the contract in order to independently develop software, right? So you can sort of keep developing the software on the implementation side, and the user depends on just the API here, and they can keep extending it as long as the API stays there. I mean, this is the principle with which we build software in any sort of modern software development, right? You have a particular version that has a particular API, and you can you can you can fix bugs if you're implementing a particular library. Say you can fix bugs, you can keep making it better as long as you preserve the API, and the client code can happily extend their application this way. And if you change the API, they release a new version, right? So the API is the contract, and this is what gives us modularity in the language, right? And this is how we build bigger software in OCaml. Okay, so to take a step back, right? So what we've seen so far is we've seen a bunch of concepts. In particular, we've seen this idea of structures and signatures, right? So OCaml itself, if you sort of look at what we've seen so far, it happens to be the stratified language, right? At the lower level, you have these values and expressions, and we have types that sort of say what the types of these values and expressions are, right? And this is at the term level, right? So term, we use the word called term just to say that the base language, that's the term level, right? At the module level, you have structures which are analogous to values and expressions here, and signatures which are analogous to types, right? At the term level, oops, our values and expressions our values are first class in OCaml, right? You can create a value, you can pass it around, you can return values, and so on. It is the case that structures are generally not first class. If structures are analogous to values, the question you want to ask is whether structures are also first class in OCaml. They're generally not first class. There is a special feature in OCaml called first class modules, which we'll not cover in this class. But we don't typically consider structures to be first class. So you need to explicitly make them first class. There is a feature called first class modules, which we'll not cover in this class. But okay, but they're sort of missing something very important, right? What is the equivalent of functions at module level. We have functions in the term language. We've used function throughout, right? Is there a notion of a function at the module level? And why would you need it, right? So it's a good it's a it's a good question to ask by itself, right? I'm just asking, okay, if these are analogous, what are these? What are the analogous things for other structures that we found at term level? Indeed, it turns out that we have a function at the module level, right? And these are known as functors. The keyword is functors. And these are functions that take structures and return other structures, right? So that's the overall idea, right? So you have this thing called functor, which we are going to see next, which takes some modules, return you some other modules, hopefully adding some value to it, right? So functors are these new concepts, right? So we are going to see syntax, and then we are going to see semantics, and we will see some examples of why you will need functors, right? Okay, so we are going to see these three things in the rest of the lecture. What is first class? First class is just anything that can be sent, anything that can be passed as arguments and returned from functions, right? So we just call them first class. So I think I haven't clearly defined the term, but that is what we mean. In particular, functions are first class in OCaml, right? You take any function, the function can return functions and then take other functions as arguments. You can do this for any function, right? But in C, you have to sort of cast them to a function pointer and use them. So here, it's sort of built into the language. That is what we do. So that is why we mean they are first class. Does that answer your question? Okay. Yeah, thanks for asking that. Sometimes if I use some term without defining it, please stop me, right? I can find a different word for that term, or I'll try to explain it, what that actually means. It's a list of first-class module in OCaml. So list values are first class, right? When I create a list, I can pass lists to other functions and return lists from other functions. But module list, right? That is not first class. So what I mean by first class modules is the thing that you write. When I write list, oops. When I write list, right? I can't. I'm creating hypothetical syntax here. Let v equals 10. So this is not a thing that we typically do, and I can't store. So this is okay. Maybe a more interesting example is. So this is not a sensible thing, right? So what I'm doing here is, if something is first class, it can go anywhere where you can expect values to go, right? I'm creating a function that, I mean, this does not work in OCaml. I'm just creating this to make a point. I'm taking list module as an argument. I'm returning you a list with two modules in it. So OCaml is a stratified language, right? You cannot mix these things together. Wherever the thing that can go here has to be a value, but this is a structure, and structure is not a value. So that is what we mean by modules not being first class by default. Let's go further. I think you will sort of see what I'm sort of attempting to convey. But this is not something that you can do in OCaml. So what I mean is, wherever you have values, you cannot use modules happily. But with first class modules, which is like an extension to OCaml, you can do something like this. Okay, taking a step back, right? Let's just identify what a functor is. What does it mean to have functions at the module level, right? Let's just look at simple functions first, right? So here is a simplest function, which is an identity function. Identity function takes some value x and then returns that value, right? It's a polymorphic function that goes from alpha to alpha. So this should be clear, right? So we want to define, what we're going to define is, we are going to define a identity functor, right? What is a functor going to do? It's going to take some module, right? And it's going to return the same module, right? And that's a functor. So let's see how to do that. First thing we do for this example is define a module type, right? I have a module type T, and the type defines two things. It has a abstract type T, right? And the module type also has a declaration which says that there is a V, a value V, whose type is this T, right? So the signature contains two things. It has an abstract type T and a value whose type is T. And here is the declaration of the functor, right? Firstly, syntax. The syntax that we use is, we still use the keyword module, right? And this is the functor name, right? The name is ID. We have to use capital I at the module level, right? And this is the argument, right? The argument says that X is some module, right? And the module type is T. The T is what I've defined here. X is this variable. So X is some module whose type is T, and this functor itself is going to return another module whose type is also T, right? Which is the same as what we do here, right? X is some module. If I make it more concrete, I can write it something like this. X is an integer, and this identity function is going to return an integer, right? This is an integer to integer function. Here I have this function at the module level which says that X is a module whose module type is T, and then the return type is also going to be T. And just like the identity function, I'm going to return the same module. I need to run this. Okay, so here we saw that the type of this term is a function type ID to ID, right? Here we say that this is a functor, right? Module ID is a functor, a function at the module level, which takes a module X of type T and then returns you a module whose type is the same as the T here, right? So this should be fairly clear, except for the new syntax here, right? We are not doing anything interesting here. We are just saying ID is this functor which takes a module, returns the same module. I am making the types concrete here, right? It's the type here that I make concrete. Okay, so now what can we do here? When you define a function, you can apply it, right? So if I do ID of 5, I get 5 back. Similarly, I need to apply this functor. This functor takes a module as an argument, right? So let's define a module first. So I define a module M such that it has two things. It has a type T, which is expected to be integer here. So we just define an alias T, which is the same as the integer type, and V is 10. So this module, right, has a suitable type for being accepted to this identity function, because the expected type is T such that there is an abstract type T and a value V, and we do the same thing here, right? The declaration of module M has the same two parts. Now we can apply it. The functor application has to explicitly have this bracket here, right? So we need it here. We don't need it there. We need it here, just so the parser does not get confused. And we are applying ID to M, so we get another module M prime, which has the same contents. Right? So if you look at this, what we get back is a module, right? Whose type, there is a type T, and then there is a value v. So it's printing just the signature here. It's not actually printing the content, it's printing the signature. Right? So here is how you would apply the identity functor. So identity functor takes a module and returns a module, right? Just like the identity function. Okay, so far it's fine. Let's now talk about something that happens, which is special to modules, right? The thing that happens with functors is that we have this notion of abstract types, right? And that sort of introduces a little bit of interesting behavior. So let's look at an example, right? So in this example, just like the identity function here, this is an identity functor. So if I pass m here, it must be the same m that comes out, right? I just name it m prime. So I know that m is the same as m prime, right? Does OCaml know that m is the same as m prime? Let's ask that, right? We know that m is the same as m prime because the functor that we defined is an identity functor. Let's ask whether OCaml knows that m dot p is the same as m prime dot p, right? So let's just ask this question. Interestingly, OCaml says, okay, the expression has type id m dot t, right? This expression has type id m dot t, but an expression was expected of type int. So what is happening here is OCaml knows that m dot b has type integer, but it is not able to identify that m prime dot v, which we know for a fact is the same module, right, is also not of type integer. That's strange, right? Why is it the compiler does not know that m prime dot v is also an integer? The answer for that is because of the fact that the type was left abstract here. So in particular, the type t, right, says that there is a type called t which is abstract. I'm not going to tell you anything about the type t. So the thing that is expected here, right, has to be of type t. It can be more specific. So the thing that we actually passed is where the type t was an integer, right? We knew something about it, but what comes out, right, is just a type t. So OCaml does not know, right? The type t that comes out is also an integer because of the abstraction. I mean, we don't want to break abstraction, so we can only assume whatever is in the specification of the module type. The module type says nothing about the concrete type of this t. So that is why, if you look at this one here, this is not integer, right? Even though this was an integer, right? The result m prime just says that it's some ID of m dot t. Actually, it doesn't know. It just says that's an abstract type. I don't know that this is actually an integer, right? That is what is causing this problem here. And that is because it's an abstract type, and that's a good thing, right? Whenever you enforce an abstraction, you don't want to break that abstraction. And that is what OCaml does. But you can ask, okay, I want to allow, I want to sort of break this abstraction in specified ways, right? I want to make things more concrete. Given some abstract type, can I make things more concrete so that I can ask this question, right? I want to be able to ask this question and check whether they are equal. How can I take something that is abstract and then make it more concrete, right? So that's really what we are going to see next. So how do we do that? So a new concept here. The concept is sharing constraint, right? So as I mentioned, the sharing constraint is going to allow you to take abstract type and make it more concrete, less abstract, right? Less abstract, more concrete. Okay, so again, we are going to just focus on this identity functor that we defined earlier. So we had a functor definition ID, which takes some module X of type T and returns the same module, and it's not doing anything interesting here, right? Now I want to actually convey the information that the type T here, right? The type T here is the same type as the type T that was passed here. That is what that was missing, right? So um, I want to convey that even though these two are abstract, I actually don't make any assumptions on what the concrete type is. I'm going to add a little bit of constraint. The constraint only says that in the result type T here, right? Whatever the type that is written here, T is still abstract, right? T remains abstract, but let me just tell you that this T is the same T as x dot T. So the way to read this is something, assume that there is a bracket here, right? So ID2 is a functor, right? That takes a module whose type is T and then returns some module whose type is T such that, here's the constraint, right? Such that the type T in this module is the same as x dot T. Right? So I don't know whether it's an onion or apple or something. Whatever it is, that is the same as the argument modules T. So okay, so I've added that constraint now, right? So if you look at the functor, it actually says that the type T here is the same as x dot T. And now we know that this particular constraint is being communicated to OCaml, right? So this type is actually more specific, right? It's more concrete than the type here. So the syntax here is this width, right? So whenever you want to add a sharing constraint, we call these things sharing constraints, but in reality, what they do is they make types more concrete, right? The sharing constraint just says that this is a type T with certain constraints such that the type T here is the same as x dot T. Okay, so now that we've added this, we can ask the question that we asked earlier, right? So now let's create a M2, which is this new functor applied to M, right? So I got an M2. Now I can ask whether M2.v is the same as n.v. So this type checks first, right? And then the dynamic semantics, we are not changing anything, so we get bool true. And it earlier used to be the case that this question was ill-typed earlier because the type equality, right? The fact that these two are equal was not known by OCaml. Okay, so last thing about sharing constraint is so in this case, right? In this case, we had a single constraint. There is one constraint here. The constraint is that type T is the same as x dot T. Perhaps I might have multiple constraints, right? What is the syntax for communicating that? And the syntax is this. So let's take an example. So I define a new type T2 such that there are two abstract types. So there is a type T and then a type U. Both these types are abstract, right? And I define a module, I define a functor, an identity functor again, right? And this identity functor takes some module x2 whose type is T2. T2 is the one that is defined here, and returns you a T2 such that the types are the same, right? It says that the type T is the same as x2.t and type U is the same as x2.u. And the syntax is this. So when you want to combine multiple constraints, you add one type constraint like this and the second constraint. You can keep adding this, you can keep adding more constraints as you want. And this is just an example to show that you can actually write down this module as it is. And this works out. And here we get the same functor which says that, oh, ID2 is a functor which takes a module x2 whose type is T2 and returns you a module whose module type, signature, has two types T and U, where T is x2.t x2 is the argument, u is x2.u. Okay, so that was sharing constraints and sharing constraints with more than one constraint. So far, right? So I've only shown you the syntax and semantics. I haven't actually showed you any useful example. So the last thing that we will do in this lecture is we will actually see what functions are useful for. So far, we've seen a lot of syntax, right? Why do you need it? So here is the problem. So let's say I want to write a serializable list implementation. What do I mean by that? I want to write a string of list and list of string functions. A string of list function takes a list, right, and returns you a stringified version of that list. So if you have a list of integers, it should return you a string which contains a list of integers, right? And similarly, I want a list of string function which takes a string version of a list, right? And then it returns you a list with those elements. So you can sort of think about this as a serialization function, right? So if you want to say print it to screen, then you can take any list and then convert that to a string and print it out. This is like input function. So you get some input from the standard input, right, from the user, and then you convert that to a list, right, so that you can manipulate it and do whatever you want with it. But the important thing that I want to do is because we have polymorphism, right? I want these functions to be defined for arbitrary type list, right? I want it to be defined on any type list. It could be defined on an integer list, string list, Boolean list, list of lists, list of lists, anything, right? How do I do that? So the key identification is that in order to convert a list to a string or a string to a list, we need to know the corresponding functions for the elements that are present in the list, right? We need to know how to convert a list element to a string and vice versa, right? So if you know how to convert a list element to a string and a string to that list element, then you can apply the same principle for all of the types, right? You know how to do contents, then you can just do it for the structure of the list. So what do I mean by that? Let's make it more concrete. So here is string of list function that works for integers, right? It takes a list L, and what does it do? It is going to create a string version of it, right? Um, so I prepend this open bracket, square bracket, and suffix it with close square bracket. And within that, I iterate over the body of the list. I convert each integer to a string, right? So if it is empty, then it's just the accumulator, which is an empty list. If it is a singleton list, then I just take the accumulator and then append it to string of int, which converts an integer to a string of x. Otherwise, I keep looping, right? So I convert x to a string. I convert x to a string, right? I prepend the accumulator. I also add a semicolon just so that it is similar to the OCaml syntax, right? And then I keep looping so that it iterates over the entire list. So what you get is given a list of integers, it prints the list of integers in a form that is that we are used to, right? Let's see how this works. So here is string of list function. So it takes an integer list and returns your string. So if I give it an integer list, it returns me the string, which is this. And this was created by this function. Okay. So here is the function for taking a string version of the list and then returning you a list of integers. The details are not important here, but what I'm doing is I'm getting a substring such that I drop the open square bracket and close square bracket. And then I split the string on semicolon. So you get a list of strings. And for each of the strings, I convert that to an integer. So I use int of string to convert each one and then I map over the list of strings to convert that to an integer. Again, the details are not important, right? So you can go through it in your own time. So the important thing is, given a string, it returns you a list of integers, right? Given the string, list of string returns me an integer list. Okay, so I can do this for this particular integer type, but if you sort of stare at it, right, the important bit is if I want to say convert this to a floating point, if I want to apply this to a floating point list, then I need to change this function, which is int of string, to float of string, right? And I need to change these functions, the string of int and string of int here, to string of float, right? The rest of the things just stay the same. So modules allow you to express this very nicely, right? So what do we need to do for any type t? We need two functions. We need a way to go from string to that type t, right? So for any type t, we need a way to go from string to that type t. We name that function t of string, and also need a way to go from that type to string. So that is string of t. So you can sort of think about this as off string function and to string function, right? So that those are the analogs. So what we've done here is we've defined a module type, and the module type sort of defines a property, right? It defines a property called serializable, right? Which is for that particular type t, there must exist two functions, right? One function to convert string to that type, and another function to convert that value of the type to a string. So we defined it. So that's there. So now what we do here is, assuming that you are given this module with this capability, you can do everything that we done earlier, right? We know how to do it for a list, and we are now given how to do it for the element, and we can construct the functionality for converting strings to lists and lists to strings. So how do we do this? So we define a functor called serializable list that takes as argument this serializable module. So this serializable module, right? The C module tells us how to convert an element to a string and string to this element. And the rest is the same as what we have seen earlier. So the important bits are these, right? The important bits are, we define a type T such that it's a list, right? It's a list of elements whose type is the same as the type in C, right? So if it is an integer, then this will be an integer list. If it is a floating point, then our serializable list will be a floating point list. If it is a string, then our list here, the type T here, will be a string list, right? And these functions are the same as previously defined. Oops. Same as the one previously defined, except that in places where we had used string of int and int of string, we use c dot string of t and c dot string of t here, and c dot t of string here. So we are actually using the stringification functions and the parsing functions from the C module. Okay, the rest, the logic stays the same. So we sort of split out the notion of how to convert a particular value to a string from the rest of the logic for list, right? So that's done here. So what we end up getting is the functor, right? Given a way to convert a particular element to a string and string to a particular element, we know how to convert a list of those elements to string and string to a list of those elements. Okay, now let's see this in practice, right? So I'm going to define one for serializable floating point list. So the way to do that is define a structure, right, whose type is floating point, and we need t of string and string of t functions, which are handily available from the standard library. Those are float of t and string of float functions. And we apply the structure, right? We are not defining it separately and applying. We are directly defining it in place. We are applying, right? We are taking this serializable list functor that we defined in the previous slide here, and we are applying it to this floating point module, right? And what you end up getting back is a serializable float list. So this is a version of a list, floating point list, with the ability to convert to a string and parse it from a string, right? So you get these functions out: float list to string and string to float list. Okay, so now I can use the functions in this module, right? So here is string of t, and this is a floating point number. So you get you take this floating point list and convert that to a string, and you can do the same thing the other way, right? Take the string, which is the floating point list, and actually return a floating point list, right? You can do this for strings. Because strings are already strings, t of string and string of t are just identity functions, right? We know this is a string, we are just going to return a string. So, and we make it concrete, the type t, we make it concrete to be a string, right? So, given a string list, we will return a string, and this t of string is given a string, it will return a string list. Okay, so to see this in practice, so here is a list of strings, which we convert to a string. And here is a string, which we convert to a list of strings. Okay. But the cool bit is this, right? Observe that the signature of serializable float list that we defined earlier, the serializable float list, where is it? The serializable float list, right, that we defined earlier, has the same signature as a serializable type, right? So a serializable type has an abstract type t and a t of string and a string of t, right? And we defined it for a floating point number here, right? And by applying this functor, we get something where the type is a floating point list, right? And we also get a string of t and t of string. In particular, this type is also a type that is suitable for application places where serializable is expected. So what we can do is we can use we can create a module that serializes list of floating points by just applying this list of floating points serializable to the serializable list function. So just because we have the same shape, right, we can keep doing this over and over. So what you get out is also of type serializable. So we can apply it. So here is what we get in turn for free, right? Because of all of this abstraction that we've applied. So we get something out, which is the type T is a serializable float list. So the way to read this, it's a bit abstract, but the idea here is it's a list of floating points, right? Given a list of floating points, it converts that to a string. Given a string, this function returns you a list of floating points. And here is an example, right? So here is a list of floating points, which I now convert to a string automatically. So this is the power of being able to abstract away the details of the implementation. Right? So you can reuse the same structure in multiple places. Observe that we've just written what to do for the outer list structures, and everything else just fell out of the fact that we were able to abstract away the details of the type. Okay, so I think that is what I wanted to say about modules. So in the exercise, in the next assignment, you will use modules and side effects. There you will use modules from the standard library. I think those are. I think you'll gain much more hands-on experience with using modules. And on Monday, right? So what we'll do is we'll have a doubt clearing session. So we will have a class where go through the lectures that we've covered so far, right, and come up with questions and um, examples that you don't understand and so on. So this is the time when we would usually have a quiz one, right? And because of how we are doing this semester, we don't have time for we don't have quiz one, but I would still like to have this review sort of class, and all of the videos are there. So I don't want to do this traditional review or going over the material again. If you have doubts, go through the videos again, but come with questions, right? So on Monday, what we will do is we'll have the entire class just for questions. And then we'll see more advanced features in OCaml for a few lectures, and then we'll shift to Prolog. Okay, I'll stop here. I still have time. If you have any questions, you can ask me. Seems like there are no questions. Okay, so go through the lectures, right? So I'll upload the video as well. Come prepared with questions for Monday's class. If you don't have questions, we'll just end the class early. Make me stay, right? So use this time. All right, so I think I'll stop here. Thank you very much. Talk to you later. Bye-bye. Have a good weekend.